movement all the time. The car is moving, the ball is flying. Seems pretty simple. But what if I told you there's a kind of secret language underneath it all? A precise code that physicists use to tell the complete story of any journey. Today, we're going to learn to speak that language, the language of motion.
So let me just start by asking you a question, a really simple one. Are you moving right now? Seriously, think about it. You're probably sitting there, maybe in a chair, thinking, no, I'm sitting perfectly still. But are you really?
Well, here's the thing. That chair you're in, it's on a planet that's spinning at over 1,000 miles an hour. And that whole planet is whipping around the sun at a wild 67,000 miles per hour. This gets us to the #1 rule of motion. It's all relative. It completely depends on your point of view.
So if we're going to talk like physicists, we can't just say something is moving. That's not enough. We have to answer a much better question. Moving compared to what? We need some kind of anchor, a fixed starting line to measure everything from.
In physics, this anchor has a name. We call it a reference point, or an origin. Think of it like the "you are here" dot on a map. Without that dot, words like left, right, north, or south are totally meaningless. It's the one thing our whole story of movement is built on.
And the funny thing is, you do this all the time without even thinking about it. Look at this example from our source material. The school is described as being 2 kilometers north of the railway station. See, the railway station is our reference point. It's our anchor. Without it, 2 kilometers north is just floating in space with no meaning. Okay, so we've got our starting point. But what about the actual trip? Let's say you go for a walk. You go all the way around the block, and you end up right back on your own doorstep. How far did you go? Well, the answer isn't as simple as you might think. It really depends on which story you want to tell. Yep, there are 2 totally different ways to tell the story of that trip. The first way is to count every single step you took along that whole winding path. But the second way, it's much more direct. It just looks at the straight line between where you started and where you ended.
All right, let's look at a picture to make this super clear. Imagine a car starts right here, at point O. It drives 60 kilometers down the road to point A, then it flips a U-turn and drives 35 kilometers back, finally stopping here at point C.
So, how far did the car go? Well, if you look at the car's odometer, it's going to tell you the long story. It'll say, we went 60 kilometers out, then 35 kilometers back. Add those up and you get 95 kilometers. In physics, we call this total path, the odometer story, the distance. But what if you just wanted the bottom line? The as the crow flies version. The shortest, straightest line from the starting point O to the finish line C. Well, that's a much shorter story. The car only ended up 25 kilometers from where it started. We call that the displacement.
And right here is the big difference. Distance, it's just a number. It's how much ground you covered, period. But displacement is a lot smarter. It knows about direction. It's the overall change in your position from start to finish.
Okay, so this whole distance versus displacement thing gets even more important when we throw time into the mix. We all think we know what speed is, but in physics, just knowing how fast you're going, well, that's only half the story. So normally, we calculate average speed by taking the total distance traveled, the odometer story, and we just divide it by how long the trip took, and that gives you a pretty good idea of your overall pace. But here's the catch. What if your journey isn't a straight line? What if you turn, or twist, or even double back on yourself? Speed, by itself, can't really describe that very well. To paint the full picture of motion, we need something with a little more oomph. Which brings us to this really cool little puzzle from the source material. I like to call it the swimmer's paradox. Check this out. Usha is in a 90-meter-long swimming pool. She swims from one end all the way to the other, touches the wall, and immediately swims all the way back to her starting block. The whole round trip takes her exactly 1 minute. Now let's analyze her swim using our 2 different storytellers. There's average speed, which, as we know, uses the total distance. But then there's this other, more precise thing called average velocity. And that one, it uses her total displacement.
Okay, let's crunch the numbers. For her average speed, we take her total distance, that's 90 meters there and 90 meters back, so 180 meters total, and we divide that by 60 seconds. That gives her a really fast average speed of 3 meters per second. But what about her average velocity? Well, because she ended up exactly where she started, her total displacement is 0, and 0 divided by 60 is 0. So she was moving like crazy, but her average velocity was 0 meters per second. It's not really a paradox, is it?
It's just physics telling two different equally true stories. So far, we've pretty much been talking about steady, constant, kind of boring motion. But real life isn't like that, right? We speed up, we slow down, we turn corners. We need one last tool in our kit to tell the story of change.
And that final tool is acceleration. Now, when you hear that word, you probably think of slamming on the gas pedal. But in physics, acceleration is any change in velocity. So yeah, hitting the gas is acceleration. But hitting the brakes, that's also acceleration, just in the other direction. And here's the really cool part. Even taking a turn at a perfectly constant speed is acceleration, because you're changing your direction, and that means your velocity is changing.
You can actually see these stories on a graph. Look at this distance time graph. A journey with a constant velocity, what physicists call uniform motion, tells a really simple story. It's just a straight, predictable line. For every second that goes by, the object travels the exact same amount of distance.
But now look at this one. An accelerated journey tells a much more exciting story. The line curves up. See how it gets steeper and steeper? That curve is telling us that with each passing second, the object is covering more and more ground. It's speeding up. That curve is the story of change.
And there it is. That's your complete toolkit for motion. To tell any story about something moving, like a pro, you just need these 4 things. You need a reference point. Where do you start? You need displacement. What's your net change in position? You need velocity. How fast and which way? And you need acceleration. Is that velocity changing? You're now fluent in the basic language of motion. So the next time you're in a car or just watching a leaf fall from a tree, I want you to ask yourself a new question. Using this toolkit, what is the real story this movement is